welcome back to the Explainer. If you're a focused learner trying to completely master coordinate geometry, you're in exactly the right place. Today, we're taking our uploaded lecture PDFs and transforming them into a complete step-by-step visual masterclass. We literally aren't skipping a single topic, definition, formula, theorem, or example from the notes. We're building this from the ground up, from moving points around to measuring the space between them and instantly decoding any graph. By the time we're done, you're going to have an ironclad grip on the 2D plane. Okay, let's look at our roadmap for today. We've got 1, mirror images and reflections, 2, deriving the distance formula, 3, applying that formula, 4, the midpoint formula, 5, quadrants and graph analysis, and 6, a final coordinate geometry checklist to make sure we caught it all.
Let's dive right into Section 1, Mirror Images and Reflections, flipping coordinates across the axes.
So this table brilliantly shows the core rules of reflection. Watch how the signs flip depending on which axis acts as your mirror. If you take a standard point, let's call it x, y, and reflect it across the x-axis, the x stays exactly the same, but the y, it becomes negative. It basically drops down below the mirror line. Now, if you take that same point and reflect it across the y-axis, the y stays put, but the x jumps to the other side, becoming negative x. It's really just a beautiful, symmetrical dance. Here is the absolutely crucial takeaway. Reflecting across the y-axis only flips the x value, which, by the way, we call the abscissa. For instance, if you've got the point 7, -8, a y-axis reflection flips it right over to -7, -8. On the flip side, reflecting across the x-axis only changes the y value, known as the ordinate. A great trick is to just keep the mirror in mind. Whichever axis is your mirror, that specific letter's coordinate stays identical, and the other one flips its sign. Okay, let's actually apply this logic to one of the trickier problems from the source material. We're given a point expressed algebraically as x plus 3, x plus 4, and we're told its mirror image about the x-axis is 5, -6. We need to solve for x. Well, remembering our rule, an x-axis reflection changes the sign of the ordinate, the y value. So negative times the quantity x plus 4 must equal our new y value, -6. We just drop the negatives, so we get x plus 4 equals 6, and simple algebra tells us x equals 2. Boom! By just understanding the reflection rule, a word problem that looks super complex actually becomes incredibly easy. Moving right along to Section 2, deriving the distance formula, finding the shortest path between 2 points. Now, what I find really fascinating about this derivation is how it proves the famous distance formula isn't some magic spell. Honestly, it's just the Pythagorean Theorem in disguise. Think about it. If you plot 2 points, P and Q, you can draw a right-angled triangle right between them. The horizontal base is simply the difference in their x-coordinates, so x2 minus x1. The vertical height is the difference in their y-coordinates, y2 minus y1. Remember a squared plus b squared equals c squared? We just plug our base and height in to find the hypotenuse, which is our distance. Take the square root of both sides, and there it is. Distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Which brings us perfectly to Section 3, applying the distance formula, putting the theorem to the test. Let's look at points A and B here. Point A is at 0, 6, point B is at 0, -2. I want you to take a second and mentally plug these coordinates into the formula we just derived. What's the difference in x? What's the difference in y? Well, if you notice that the x-coordinates are both 0, meaning we really only need to look at the y-axis, you are absolutely on the right track. 6 minus -2 gives us positive 8. Squaring that gives us 64, and the square root of 64 brings us right back to 8 units. Or, you could just count the spaces on the y-axis. 6 units above 0, 2 units below, 8 units total. Now, this brilliantly illustrates the toughest problem type you're going to face, the equidistant problem. The lecture asks us to find the variable k when point P is exactly equidistant from point A and point B. How do we do this? We just set 2 distance formulas equal to each other. Because both sides are trapped under a square root, we simply square both sides to remove the radicals. Then we expand the binomials, combine our like terms, and look at that. It simplifies down to a beautiful, clean quadratic equation. 2k squared minus 12k plus 10 equals 0. From there, it's just basic factoring to find your answers. But remember, the distance formula goes way beyond just measuring a single line. It's actually your master key for identifying 2D shapes. If a question throws 3 or 4 vertices at you and asks, hey, what shape is this? You just calculate the distance between all the points.
If all four sides are equal and the diagonals match, you've proved it's a square. If only two sides are equal, it's an isosceles triangle. You're basically using geometry's tape measure to prove the identity of the polygon.
All right, let's jump to section 4, the midpoint formula, finding the exact center. The definition of a midpoint is exactly what it sounds like. It's the point exactly in the middle of a line segment, dividing it into two perfectly equal halves. And the formula? Elegantly simple. You literally just find the average, add the two x coordinates together and divide by 2. Then add the two y coordinates together and divide by 2. That's the whole shebang. You're just finding the middle ground.
Let's test this out immediately. We've got point A at -2, 8, and point B at -6, -4. Take a quick second to mentally average the x values and then average the y values.
Okay, let's see how you did. For the x coordinate, -2 plus -6 is -8. Divide that by 2, and we get -4. For the y coordinate, 8 plus -4 is 4. Divided by 2 is 2. By simply adding the values and cutting them in half, we find our exact middle ground right at the coordinate -4, 2.
But watch what happens when we work backwards. In one of our lecture problems, we're given one endpoint, point A at 5, 7, and we're given the midpoint at 17, -4. We need to find the missing endpoint B, which we'll call x, y. We just set up our formula, x plus 5 over 2 equals 17, multiply by 2, subtract 5, and our missing x is 29. We do the exact same thing for y plus 7 over 2 equals -4, multiply by 2, subtract 7, and y is -15. Just like that, we've used algebra to reveal the missing endpoint.
Almost there. Section 5, quadrants and graph analysis, navigating the Cartesian plane. First things first, we've got to lock in the vocabulary. The abscissa is just the formal name for the x-coordinate. It represents how far a point is perpendicularly from the y-axis. The ordinate is the y-coordinate, representing the perpendicular distance from the x-axis. Now, these two vocabulary words appear constantly in assertion and reasoning questions, so you really want to commit them to memory. Just remember, abscissa means x, ordinate means y. Now, this table is your ultimate cheat sheet for figuring out exactly which quadrant a point lives in without having to draw a single graph. Quadrant 1, all positive. Quadrant 3, diagonally opposite, all negative. Quadrant 2 has a negative x and positive y, and quadrant 4 is positive x, negative y. So if a test question asks where -6, -7 lives, you know instantly, 2 negatives means it is parked squarely in quadrant 3. Let's solidify these core rules for axes placement. If a point is sitting flat on the horizontal x-axis, it hasn't moved up or down at all, right? So its format is always x, 0. If it's on the vertical y-axis, its format is always 0, y. And that exact spot where they cross, that's the origin, 0, 0. Grasping this logic will instantly solve those tricky true or false homework questions about point locations and axes distances. Finally, Section 6, Final Coordinate Geometry Checklist, verifying your mastery. Okay, we have completely mapped out the lecture notes today. We covered mirror image reflections across both axes, we proved the distance formula using Pythagoras, calculated distances and solved for k, we learned to identify shapes by measuring their sides, we conquered the midpoint formula, both forwards and backwards, we defined the abscissa and the ordinate, and we decoded the geography of the 4 quadrants. Review this checklist. If you can confidently explain every single bullet point on here, you have fully extracted every ounce of knowledge from today's source material and verified that absolutely nothing was missed. You, my friend, are officially a master of this topic. As we wrap up this explainer, I want to leave you with a provocative thought. We've spent this entire session mastering a flat piece of paper, an x and a y-axis, but we live in a 3-dimensional world, right? So how might these exact same formulas, distance, midpoint, reflections, evolve when we add a z-axis to the mix? Ponder how these 2-dimensional foundations are the absolute key to building out the 3rd dimension. Keep exploring, keep questioning, and I'll catch you in the next explainer.